And I'm going to stop my video to save bandwidth. Okay, and so we're going to start this class by doing a quick review of the things we learned in Quantum 1, and not in the same order, though. We're going to start with the postulates of quantum mechanics. Okay, and so the first one is that the state of a system is represented by a non-null ket. Often we will use psi for that non-null ket. And a reminder, this is an element of a complex linear vector space. Okay, with an inner product. Not all vector spaces are endowed with an inner product, but in quantum mechanics, we assume there is one. So complex means that you can multiply any ket by a complex number. So can multiply by a complex number. And linear just means it obeys the usual addition properties of a vector. Oops, addition. And the fact that it's a vector space, among other things, means that you can find a basis. That is a set of vectors that you can build any other vector out of by adding them together. And the inner product means that for any two kets, you can form a complex number, like so. So this is a complex number. With the property that if you take the inner product of a ket with itself, that's real and positive. With one exception, and that's the exception where the ket psi is the null ket. So unless psi equals 0 equals null ket. Okay, and the fact that you can multiply by a complex number is a little bit tricky, because if you do multiply a ket by a complex number, it's physically the same thing. So if I multiply psi by c times psi, where c is just a number, these are the same physical state. So you might ask at this point, well, if they're the same physical state, why don't we just always choose the complex number so that, for example, the psi inner product is equal to 1? And there are 3 reasons not to do that, 2 of which we learned last semester and 1 of which we will learn this semester. So here are 3 reasons not to just define that all of our kets have inner product with themselves equal to 1. Okay, so naively you could do that, because you could just choose C to make it so here. Just choose that complex number. But 3 reasons not to do it. First of all, there are some kets that can't be normalized. And technically, these kets are not in the Hilbert space, but we still use them, because they're very convenient idealizations. So these include the eigenstates of momentum and position. Okay, and these are idealized kets They don't actually exist in the Hilbert space because they don't have a finite norm, but we still use them. Another reason, and this has to do with one of the other postulates that we'll review in a little bit, is when you make a measurement, the norm changes. So the norm, psi, changes when you make a measurement. Now, you can always change it again after you've made the measurement, but at least in the mathematical process of describing how measurements are made, we're going to want to change the norm of the state. And the third one, which we haven't gotten to yet, and we will, is that sometimes it's just not very convenient to choose the norm to be 1, even if you can. And a great example of that is perturbation theory, which we will get to next week. Perturbation theory uses kets that do not have norm 1, just for convenience in making the math nice. Okay, so those are the 3 reasons we don't choose the norm to necessarily be 1. So that's postulate 1. This is telling you what the states of the system are. Postulate 2 has to do with what things you can measure. So observables, things you can measure or observe, correspond to Hermitian operators. But not just any Hermitian operators. They have to have the property that their eigenstates can be chosen to form an orthonormal basis. So whose eigenstates, I will often just write E states, can be chosen to be a complete orthonormal basis. Okay, and complete orthonormal basis takes too long to say. And so I say this as just orthobasis. This is not a completely standard piece of terminology. If you say orthobasis outside of this class, people might look at you funny, but they will probably figure out what you mean. Okay, so what that means is, let's say I have an observable A. The orthobasis states can be written like this. Okay, so the fact that these are eigenstates means I have an eigenvalue alpha. And so it satisfies this equation. A here is our observable. Alpha is our eigenvalue, which is being used as a label for the state. But maybe some states have the same eigenvalue label, and so you need other labels that we can call degeneracy labels. And there's going to be a different degeneracy label for each alpha, for each eigenvalue. Now, it might be that some of the eigenvalues are degenerate and others aren't. That's a very common situation. So some of the alphas won't need a degeneracy label, but others might. So those are the eigenstates. And the fact that they're orthonormal just means if I take the inner product of any 2 of them, so one of them I'm putting primes on to distinguish from the other one. Okay, it's orthonormal if this is equal to 1, if and only if the labels are all the same. Okay, that's the Kronecker deltas. So this is orthonormality. And completeness means if I sum over all of them, I have to sum over all the labels and the degeneracy labels of the ket followed by the bra. That's an operator. and it's equal to the identity operator, for which I usually write the letter I. Sometimes I'll just write 1, with the understanding that if I write 1 and it's an operator, then it's the identity operator. So that's completeness. And it's a very common thing that when you're stuck on trying to prove something, completeness might be a good idea to try. Okay, now that was assuming when I did the sum that alpha was a discrete label, but alpha might also be continuous. So if alpha is continuous, for example, position, the position operator or the momentum operator, or the position and momentum eigenvalues, okay, then instead of doing a sum, you are instructed to do an integral instead. So you integrate over alpha. And instead of the Kronecker delta, delta alpha alpha prime, you're instructed to use a delta function, a Dirac delta function. Okay, so together, those continuous ways of doing things, that's called Dirac orthonormality. Okay, and if the row of alphas are continuous, then you do the same thing. So I'll just write similarly for the row of alpha labels. All right, so that's postulate 2. It's telling you that associated with an observable is an operator and is associated a complete orthonormal basis. You get both of those if you have an observable. Okay, postulate 3 is telling you if you do measure an observable, what can you get? And the answer is very simple. The only thing you can get is one of the eigenvalues. So the allowed results of measurements of A are the eigenvalues, alpha. So for example, if you measure the position, and let's say I'm just going to measure the position in the x coordinates that has eigenvalues that are the numbers x, and so you can get any real number that you want. If you measure the position in three-dimensional space, so you're measuring the vector position operator, for which my notation is the capital R letter, then the eigenvalues are the vectors in three-dimensional space. So those are both continuous, but an example where you only can get discrete things is angular momentum. And so for example, if you measure the z component of the total angular momentum, we usually use the letter J. This has eigenvalues that are h bar times m, where m must be an integer divided by 2. So there's no way to measure an angular momentum and get anything that is not an integer divided by 2 in a single measurement. All right, postulate 4 is telling you if you do make such a measurement, what are the probabilities that you'll get different outcomes? So if you're in a state described by a ket psi, and you measure an observable, A, then the probability for each of the possible outcomes, so the result alpha, is, and I'm going to usually use curly P's for probability. Curly P, probability of getting alpha, is you need to sum over all the different degeneracy labels for that alpha, because there's more than one way you can get alpha. So you have to sum over all of them. And you sum over the inner product of each one of those states with the state that you happen to be in, psi, and you square it. So a key thing to note is that it's probably easy to remember that you're going to have to sum over the degeneracy labels, but the key thing is you sum over them after squaring, not before squaring the inner product. Okay, and then the result, you can write a different way. You can write it as psi p alpha psi, where that p alpha is an operator. It's the projection operator, which is written like this: sum over rho of alpha, the degeneracy label of alpha rho alpha, alpha rho alpha. Okay, so if you just plug this right here into here, that just gives you this. It's the same thing. And so you can write the probability in terms of these projection operators. All right, so notice that projection operators have a very special property. Any projection operator, if you square it, gives you back the original projection operator. All right. Another thing to notice is that when I wrote this formula, I did assume that psi had norm 1, which, remember, I made a big deal earlier saying psi doesn't have to have norm 1. So what that means is if you're going to apply this formula, you have to first make sure that your state has norm 1. Okay, so this assumes that psi inner product is equal to 1. But if not, so otherwise, all you have to do is divide by that norm. So otherwise, the probability of getting alpha you can write by the same thing. So once again, I'm going to sum over all the inner products of the different eigenstates for the operator A with the state we're in squared. And now I just divide by the norm, psi. Okay, so that, if you have trouble remembering it, one way to think about this is that since the norm of psi is not physically relevant, and there are two psi's in the numerator, I can get rid of the normalization and make it manifestly not dependent on the normalization by dividing by two psi's in the denominator. And the only way to make a number out of two psi's is to take the inner product. Okay. Good. So that's probabilities of measurements. And then there's the postulate 5, which famously many people want to do away with and replace. And postulate 5 has to do with what happens to a state after you make a measurement. This is sometimes known as the collapse postulate. This says that after the measurement, let's say you did a measurement and you got the result alpha. So since there are often more than one different alphas that you can get, you might have to analyze a problem from the point of view of many different alphas. In any case, the state after the measurement is given by the same projection operator acting on psi. Okay, so the projection operator here is good for two different things. One is it gives you one formula for the probability. Of course, you can just write this down directly if you want. You don't necessarily need the projection operator. But if you do it in terms of the projection operator, then you also are able to derive the state after the measurement. It appears in both places. Now, when you do that, the projection operator acting on psi is, again, as I mentioned before, not normalized. Okay, this does not have norm 1, but that's easy to take care of. There's a normalized version of it. Okay, and so the normalized version is I just take that same state and I'm going to divide by a number. And the number we're going to divide by is the norm of P alpha psi. So I write here psi P alpha psi. So technically, when I wrote that down, I maybe should have, when I compute the inner product, I should have maybe written P alpha dagger there, but it doesn't make any difference because another property of P alpha, maybe I should have written this up here, also P alpha dagger is P alpha. In other words, it's Hermitian. Okay, so P alpha dagger is P alpha. That means this dagger I didn't necessarily have to write, which means P alpha is, according to this, just equal to P alpha. And so another way of writing this is I could have written just one P alpha in the denominator. Okay, of course, if you're doing a computation, it won't really matter. But the nice thing about doing it this way is it's just the minimal way of writing it. Okay, that's postulate 5. It tells you what happens when you make a measurement. And the last postulate is what happens to states, or how do states change when you don't make a measurement? And that's time evolution. Okay, and time evolution says the ket obeys a differential equation, which fortunately is a first order differential equation. It says IH bar times the time derivative of the ket. And so I'm indicating that my ket has a time dependence by making it a function of t. That's equal to a certain observable operator called the Hamiltonian acting on the same ket. Okay, so H here is Hamiltonian. And the eigenvalues of the Hamiltonian are the energies, by definition, of the system. And so they may be discrete, they may be continuous. It depends on the physical problem that you're trying to do. In general, if it's a bound state, then the energies will be discrete. If it's a non-bound state where the particle's free to wander off to infinity, then the eigenvalues, the Hamiltonian, will be continuous. Okay, any questions on our review of the postulates of quantum mechanics before we move on? I should say that you should feel free to interrupt me at any time with questions, even if we're on Zoom here. No? Okay. So the next thing I'd like to do in our little review here is talk about wave functions. Okay, and so with wave functions, the strategy is we start with a particular orthonormal basis. So we start with position eigenstates. And so if we're working in a three-dimensional universe, they're labeled by some vector that tells you what position you're talking about. And so this is defined to be the state where the particle is known because it's been measured. usually, to be at the position labeled by R. Okay, so we start with those orthobasis kets. And then if we do the inner product with the ket describing the state that we happen to be in, that by definition is the wave function. So I've written it as a function of the vector position, but of course, I could instead write it as a function of the corresponding rectangular coordinates or the corresponding spherical coordinates, or in principle, the corresponding cylindrical coordinates, although we won't use cylindrical coordinates much in this class. Okay, and then the nice thing about using wave functions or the position representation is that the operator for position corresponds to just the ordinary number vector position, right? So in any expression written in terms of wave functions, when you would normally write this, you can write just the ordinary number position. And then for the momentum, you would write minus I h bar times the gradient as a differential operator. So when I write this, what I really mean is these on the left are operators. Okay, and on the right, we're talking about their action as differential operators, not Hilbert space operators, on wave functions. Okay, so this means I just take the gradient of my wave function. As an operator, it's more of an abstract thing. This is acting on kets. So for example, one thing we can do is suppose we integrate over all possible position vectors of the complex square of the wave function squared. So that, well, the complex square of the wave function. So one way to get something out of this is to write it like this, integral d3r psi r psi. So what I've done there is I've used the definition of the wave function. Okay, and then that's equal to just psi inner product psi. So I get rid of the integral d3r and I get rid of the bra and ket r. So what I've really done there is I've used completeness. Notice this is the Dirac orthonormality version of completeness. So I'll write here Dirac version. Dirac version is just telling you that it's a continuous thing that you're integrating over. And then if the ket has been normalized, which you can always do, but isn't necessarily automatic, then that's just equal to 1. So I'll say here, if normalized. Okay, so oftentimes we will find it convenient to work in terms of wave functions, but you have to have the ability to translate back and forth between wave functions and kets. And a lot of times we'll just sort of write that down because it will be familiar to us, but it's a good idea to keep in mind that the key thing, besides the definition of the wave function, the key thing that you're always using when you translate between bras and kets and wave functions is you're always using completeness. That's how you get this product integrated over all r's is equal to the identity operator. All right, so here are some important theorems. Last semester, we spent some time proving some of these theorems. They're actually, usually in quantum mechanics, anything that's really important as a mathematical theorem can be proven in 1 or 2 or 3 lines, once you have all the definitions set up at least. So one is all eigenvalues of a Hermitian operator are real. So if you're working a problem, sometimes that gives you a consistency check that you can use to your advantage. It may be that when you're doing intermediate states in a problem, it may be that it's not so obvious that the number you're going to get out is real. But if you're computing the eigenvalues, or for that matter, it turns out it follows from this, the expectation values, which I haven't defined in our review here, but I will. So expectation values too. You have to get a real number. And so if you didn't get a real number, something went wrong and you can hope to find the mistake. Okay, so that's one important theorem. Another important theorem is if A is Hermitian, so that includes all observables, but not all Hermitian operators are observables. Anyway, if A is Hermitian, and you know 2 eigenkets of it, let me call them V1 with eigenvalue alpha 1, and V2 with eigenvalue alpha 2. And we'll assume that alpha 1 is not equal to alpha 2. Then the 2 kets have to be orthogonal, which means their inner product has to be 0. Okay, so we often use this because we'll identify some operator, we'll figure out its eigenvalues, and then any 2 of them, any 2 of the eigenvectors corresponding to different eigenvalues have to be different, have to be orthogonal. Okay, here's another good theorem. Let's say I have a bunch of observables. I'm going to call them A, B, and C, etc. We're not necessarily committing to a specific number, but we're saying that they are observables and that they all commute. And a synonym for that is that they're compatible. Compatible literally means the same thing as they all commute. Okay, then there is an orthobasis of common eigenstates. In other words, eigenstates that are simultaneously eigenstates of all those operators, and they form a basis, right? And so we can write them like this: alpha, beta, gamma, those are the eigenvalues. Okay, and so there is, this theorem doesn't necessarily tell you how to find them. You might have to do some work to find them, but you're guaranteed that such a thing exists. So a closely related thing is the concept of a complete set of such observables. So a complete set of commuting or compatible observables. And that takes way too long to say, so we always say it as CSCO. Is a set of such operators, A, B, C, but there's almost always a finite number of them, and it's usually 2 or 3 or 4 or something like that, not an enormous number. Is this set of operators such that the states mentioned in this theorem, alpha, beta, gamma, don't need any other labels. So each one of those states has no degeneracies. And so it's uniquely determined. In other words, if I tell you what alpha, beta, gamma are, if I tell you what all those eigenvalues are, then you know exactly which state I'm talking about. Okay, so for example, for a free particle in 3 dimensions, then it's very easy to write down a complete set of commuting observables, namely just the operators x, y, and z. Because if I tell you what x and y and z are, I've told you everything there is to know about that state. But there's a different set of complete setting of CSCO. I could instead decide to tell you what the momenta are for that particle. Okay, or, and this will be much more common this semester, instead of telling you those 3 things, I could tell you the Hamiltonian eigenvalue, the angular momentum squared eigenvalue, and the z component of angular momentum. So no matter how you do it, there are 3 operators in the complete set of commuting observables, but you have a different choice, and a lot of times you want to translate between one choice of complete set of commuting observables and the other. And behind the scenes, the way you always do that is to use completeness, because they both have an ortho basis. And so you can use the ortho basis for one to translate into the other using completeness. So that's for a free particle in 3 dimensions if it doesn't have spin, but for example, electrons have spin. So if the particle has spin, you might have to add to that spin. And there are 2 operators that you add to the CSCO to get spin. One is the total spin squared, and the other is the spin in the z component. Now, this total spin squared is kind of trivial, because unlike L squared, which can be different for different states, the total spin squared is always the same. Okay, so S squared is fixed. It never changes. It's the same for all states. That's sort of the definition of spin, is the part of the angular momentum that you cannot change. Okay, on the other hand, the z component of the spin the spin can point in different directions. And so that's why the z component can be added to your complete set of commuting observables. But for example, if I've committed to this and that as my complete set of commuting observables, then I can't add L sub x or S sub y, because they don't commute with all these operators, and therefore I've exhausted the operators that I can add. Okay, so complete here. Complete means that I've gotten rid of all the degeneracies. In other words, if I've listed all the eigenvalues for you, I've uniquely determined the state. This complete, it's confusing, has nothing to do with the completeness of the ortho basis. That's a different complete. All right, any questions on that so far? All right, so let's talk about some typical problems that one encounters. And so because quantum mechanics deals with probability, a lot of times we have statistics that we have to do. One statistical thing that we might want is the expectation value. So the expectation value of an operator A in a state psi is defined to be the sum over all the possible outcomes of the measurement, alpha, times the probability of getting that outcome, times the actual value of the outcome, alpha. And so if you go back to the postulates of quantum mechanics, you find out that you can write it like this. Okay, that's using completeness backwards. And this is often just written as angle brackets for alpha, but you should be careful that even though that doesn't make reference to the state psi, it's supposed to be understood by context. So if I just write angle bracket of an operator, it's always a fair question to ask, what state is that you're evaluating it in? Okay, that's expectation value. Then there's the uncertainty. The uncertainty of A in the state psi written like that is equal to the expectation value of the operator squared minus the square of the expectation value, and then you take the square root. By definition, this is always a number larger than or equal to 0. Okay, because you're taking the square root. And among the things we proved are the uncertainty principle. So if you take the product of a position and a momentum, that's always greater than or equal to h bar over 2, no matter what state you're talking about. And more generally, for any two operators, we proved this is greater than or equal to 1/2 times the expectation value of the commutator, right? Which in the previous example, in delta x delta p, this is just h bar. This is h bar, IH bar. Okay, so another thing you can ask is, if you're in a state psi, what's the probability of finding yourself in another state, a different state? Which is, unlike in classical mechanics, not always just 1 or 0. So let me call the other state phi. First of all, if I'm asking what's the probability, I need an observable to go with that. And the observable is this operator. It's the projection operator onto the state phi. And then from the postulates of quantum mechanics, the probability is this. It's the inner product of the state you're in and the state you're going to squared. Okay, another thing that the postulates of quantum mechanics tell you is that afterwards, after you made the measurement, if you indeed found that you were in the state phi, then the state is phi, because you measured it to be there. So the key thing is to remember about this is that measurements change the state. Okay, the state changed by making the measurement. So in fact, there are two kinds of ways, two very different ways a state can change in quantum mechanics. Two kinds of ways a state can change. One is measurement. If you make a measurement, you will often change the state. That's postulate 5. And what we got from that postulate is that psi changes into the projection operator for alpha times psi. The other way is postulate 6, which is time evolution without a measurement. Okay, and there, psi changes into a unitary operator. UT to T1, so that depends on the starting and ending times. for psi. So this is saying if you start at time t1, I should have here put that this is the state at time t2. Okay, and so this is a unitary operator. And just to prove that postulate 5 is nothing like postulate 6, remember that P alpha is a Hermitian operator. And it's very rare that Hermitian operators are also unitary, or unitary operators are also Hermitian. In fact, the main example of that is parity. Okay, so you have two very different ways the state can change. The last thing I think I'll say today is oftentimes what you want to know is what are the allowed energy levels. This is another common type of problem. What are allowed energy levels? And we said before that the energies are the eigenstates of the Hamiltonian. And so what you're going to do in that case is solve this equation some way or another. This is the eigenvalue equation for energies. I've put in there a possible degeneracy label for the energies. And last semester, we did a bunch of examples where we could do this exactly. We did free particle, we did the harmonic oscillator, we did the hydrogen atom. And a lot of the things we're going to be doing this semester are situations where you can't do it exactly, but you can do it approximately. So this might be matrix or differential equations. That have to be solved. And you often need approximation. It's just too hard, too difficult to do it exactly. All right, so in this class, we're going to be doing perturbation theory. That's one way of getting an approximate answer. We're going to be doing the variational principle. We're going to be applying both of those to understanding the fine structure and the hyperfine structure of the hydrogen atom. We'll be understanding the helium atom, and then we'll be talking about scattering problems, where again, in scattering problems, you usually can't find an exact result, but you can find an approximate result. All right, we are out of time for today. A reminder that you have a homework set that is on the course webpage, which you can download, and it's due a week from today. This is intended to be a review homework set. In fact, 2 of the problems are from the final exam in Physics 660. So again, it's a good idea to not leave that till the night before in general for homework problems. So make sure you take a look at it, and I'm always available to give advice on homework problems, especially if you've already tried it and you get stuck. A great kind of question you can ask is, I tried this, here's where I'm stuck, what should I do? And sometimes the answer might be, keep going, you're doing it the right way, but other times I might be able to tell you, oh, here's actually an easier way. So do try to take advantage of the ability to ask questions in this class. All right, any questions on today's lecture or anything else having to do with how this class is going to work? All right, if not, then I will see you on Zoom on Friday, and then hopefully in person next Monday.
Thank you, Dr. Martin.